All right, let's continue our exploration of carbonyl compounds, the aldehydes and ketones, now with nitrogen nucleophiles. Last time we looked at oxygen. And we're going to see that when we take a nitrogen nucleophile, specifically a primary amine, meaning a nitrogen that has two hydrogens and then an R group, with a primary amine, we'll get a variety of different options out. If your R group is a carbon-containing unit, you'll get what's called an imine. If you have a hydroxy group on your nitrogen, it is called an oxime. And if you have an amine on your amine, it is called a hydrazone. So there's a variety of different synthetic options available to us here using primary amines. And so this reaction will replace the oxygen in acidic conditions. We can take a look at the mechanism. We'll use acetone because why not? R groups, it's fine. We're going to see that this mechanism will be very similar to our kind of generic mechanism, except we're actually going to have the first step being the nucleophilic attack. We're not going to protonate anything first here. Because amines are bases, they're what's likely to already be protonated, so that's a step we're not going to focus on here. So what's going to happen is our nitrogen goes ahead and opens up our ketone. In this case, could be an aldehyde as well. In doing so, we'll have our protonated amine species. Here we have an O minus. And so as we can see here, we have something that's protonated in a positive charge right next to something that's negatively charged. We can do what's called a proton shift, but for that we're going to have to first go ahead and show the steps out, mechanistically speaking. Afterwards, we can just kind of cheese it and say proton shift. Yeah, the proton moves over, but we're going to show that here. So generally speaking, you're going to end up having protonated amine species within your reaction vessel, because amines are bases. We're doing this in acidic conditions. So our protonating agent will be an amine. And so we're going to go ahead and protonate that oxygen there, the negative charge. And we're going to grab that off a protonated amine that happens to be floating in our solution. And in doing so, by the way, these are, of course, equilibrium reaction arrows. We will have now an OH there, along with our protonated. I'm going to go ahead and actually just switch the order here. We have our R group and our H. We're going to now have our amine come back, and it's going to now deprotonate the protonated species, restoring that to a neutral compound. And now we are left with what is called, it's very much like a hemiacetal or hemiketal in this case. This is called a carbinolamine. So another fun name for us to learn. And this is kind of our analogous to the hemiacetal or hemiketal idea, where we had one hydroxy and one ether on our species. In this case, now we have the hydroxy and then the amine on the same one. And so it's called a carbinolamine. Since our goal is to get rid of this oxygen, our next step will be taking in that extra, again, we have that protonated amine that we just generated. Again, by removing the proton from the protonated ammonium there, we have now generated our acidic species. So we're going to go ahead now and grab that proton and put it onto the hydroxy group there. And so much of this is now the same as all the other mechanisms for nucleophilic attack, right? So we're going to have our OH2, we'll say H2O, why not? And it's ready to go. And now the last step here is going to be a little bit different. Because we're going to end up with this double bond here, we're going to actually just have the nitrogen electrons close down and kick out the water. We have a leaving group here. Remember, protonated alcohol is a very good leaving group. So it's going to go ahead and leave then. We're going to form a double bond to that nitrogen. And now we have the protonated form, which we can then, again, go ahead and use. I'm going to move this arrow up just so we have our amine here that's floating around in solution. We'll go ahead and grab our proton, leaving us with the whatever it may be, imine, oxime, hydrazone, whatever your R group happens to be. We will end up now with our group. So this is our product. Hooray! Let's go ahead and go over the mechanism again. So first step, this is one point of difference. We have a nucleophilic attack happening. The protonation that's happening, because all acid catalyzed steps should have protonation as their first step, that's just protonating that other amine that happens to be around. This amine here, whatever it happens to be. So we have, technically speaking, here is our acid. Why don't we use, I don't know, HCl? It's going to go ahead and grab that. That's technically the first step. But we don't need to show that, so we can actually just start with the nucleophilic attack. So with that out of the way, our amine attacks the carbonyl, opens it up. We now have the protonated amine species and then the alkoxide. Alkoxide is less stable, so it's going to go ahead and grab a proton from the protonated amine that's floating around, thereby regenerating more of the amine, which we're going to use as a base in the next step. That amine comes now and deprotonates the amine attached to our carbonyl. We are left with our carbinolamine then. And then in order to eliminate it, we're going to go ahead and protonate the alcohol using a protonated form of the amine. So notice that the amine is also the catalyst here, right? It's acting as the acid and base carrier. Next step, our amine closes down to form that double bond to the nitrogen and kicks out the water. And another molecule of the amine will come and deprotonate it, thereby giving us our product, whether that product is an imine, an oxime, or a hydrazone. We can do just a couple of examples here. Say we have benzaldehyde, and we're treating this with methylamine in acidic conditions. We're going to replace our oxygen with the nitrogen and then whatever else happens to be there. The hydrogens are going to go away, so the methyl group is still going to be there. And we still have our H here. And so we will make an imine in this case, because we had a methyl group on our nitrogen. If we instead had hydrazine rather, and H2 and H2, two amines put together in acidic conditions, we will end up with the hydrazone. Everything stays the same. We just have our R group that can be different. And so, with this is kind of our first case of nitrogen nucleophiles. We'll see in our next step, in our next video rather, what happens when we have a secondary amine. These were primary amines. Primary amines have two hydrogens and one R group. We'll see in our next video secondary amines which have two R groups. And we're going to actually get a different product in that case. And so we'll see that in the next video.